Hello, in this video I will briefly explain how the analysis of variance works in the factorial design setting. When we talk about analysis of variance, we oftentimes only say Anova, which is the abbreviation. In Swedish this is called Variance-analys, eller bara Anova. This is an alternative and more general method to help us decide if effects are statistically significant. This is an alternative to calculating the standard errors of the effects and setting up a confidence interval where effects that lie within this interval are considered inactive, and effects outside of the interval are considered significant or active. And some of you may have encountered this alternative method in other courses, but in this course we're going to stick to the analysis of variance method because the software we use will use this method in the analysis. So let's start by looking at an example from the course book. This example is about choosing a specific material type in battery design to get as long battery life as possible. So in this example we have two experimental factors. Each factor is on 3 levels, and we have 4 replicates for each treatment. This is a full factorial design. We have 2 factors, 3 levels, and 4 replicates for each treatment. So we can see we have the material type here with 3 levels, 1, 2, 3. This is a qualitative factor which we can control for the purpose of this experiment. And then we have the temperature, which normally cannot be controlled when we run the batteries, but we can control it in the experiment on 3 levels. So we have 15, 70 and 125 degrees Fahrenheit here. And we subject these battery types, the 3 different types, to different temperatures, and we record the battery life in hours. So how do we proceed with the analysis of this example? Well, we can look at the values in the table and try to see if there are any differences depending on the rows, that is material type, or depending on the columns for different temperatures, and so on. But how do we know that these potential differences are systematic or significant, or if they are only due to random variation? Well, in this case, the analysis of variance is the procedure that we use to formalize this analysis. So we're going to start by describing each observation in this table according to a model assumption. In this case, we use what is called the effects model. So we can then say that each observation of the battery life is based on one complete, or like an overall average life for batteries, and then plus an effect for level I for the row factor A for the material types in this case, plus an effect for level J of the column factor B, which is the temperature, plus an interaction effect between levels I and J of the row and column factors, the material type and temperature. And then we also have a random error component for each replicate K. And observe in this example, for the battery life example, we have 3 levels on tau on the row factor. So small a here is 3. The same goes for small b is equal to 3, and small n is equal to 4 because of the 4 replicates that we have. Okay, so what we will try to do is to perform a form of hypothesis test. One for the row factor, one for the column factor, and one for the interaction between row and column factors. So if we take the row factor as an example, we set up a null hypothesis is that None of the tau values, none of the, let's say, the row factor effects are different from 0. All of them are 0, and one alternative hypothesis is that at least one of the tau i's are different from 0. And the same procedure goes for the column factor and for the interaction between row and column factors. So what we will do in the Anova is then as a form of hypothesis test related to these 3 components. Okay, first some explanations of notation that you will need to understand to follow the example in the course book, which is more complete, and also to follow a little bit of the formulas that will come on later slides here. So we can try to form first an average of all observations for material type 1. So all of these observations, we can calculate the average of them, and we can call that y bar 1 dot dot. We can also calculate the average of all observations for temperature 2 or 70 degrees Fahrenheit, which are these observations, and we can call that average as y bar dot 2 dot. And we can also calculate the average of all observations of material type 3 and temperature 3 or 125 degrees Fahrenheit, which is this cell here, these 4 observations, and we call that y bar 3 3 dot. Okay, so these short notations are used in the coming formula on the slide. Next slide. Okay, so try to here visualize all the variation among the observations. So we call this sum of squares. So in this case we have the sum of squares of each individual observation minus the total average of all the observations. And we square those distances, and we sum over all the observations we have. So this is the first component here. And so the individual observations minus the overall average, we square that, and we sum over all replicates, all rows and columns. In this case, we will try to divide this variation into pieces that can capture the variation which is due to material type, or due to temperature, and due to the potential interaction effect. There is also variation due to random noise, which cannot be explained, of course. And if we take a look at these formulas, we can see that here we have tried to divide this. I will not go into detail here, but we can see that we can divide this total sum of squares into pieces or parts. One part being a sum of squares related to rows, or the factor A material types. One part which is a sum of squares related to columns, or factor B temperature. One part which is a sum of squares related to the interaction between factor A and B. And one which is a sum of squares related to the error. And we can call these SSA, SSB, SSAB, and SSE. So what we want to do now is to try to test if the parts of variation that are related to effects, that is material type, temperature, and interaction, if they are considerably larger than the variation part due to noise. To say in simple terms, that's what we want to do. And in order to do that, we need to construct some form of hypothesis test. Now, moving on, what we can easily do, and just to explain some parts of the calculations that are needed, we need to calculate a lot of averages. Going back to this formula, which you can see here, we can say that we have row averages, which we need in these areas of the formulas. We can calculate column averages. we can calculate cell averages, and we can calculate a total average also. So basically what we don't know is the individual observations, which we of course need to have also, and in order for us to calculate the total sum of squares and divide them into these parts. So moving on then to the Anova table. The Anova table is sort of a partitioning of the total sum of squares due to or into different components. So you see here you have the source of variation, you have the total sum of squares, which in this case is 77,646.97. And we can divide that number into components for one component for error, one component for the A-B interaction, one component for the temperature, and one component for the material type. And we have the sum of squares here, which you can consider to be sort of a measure of variation or variability. We also need the degrees of freedom, which we can calculate as the for the material type as the number of levels minus 1. We have 3 levels, minus 1 is equal to 2. So we have 2 degrees of freedom for the material type, we have 2 for the temperature. For the A-B interaction, we have A minus 1 times B minus 1 is equal to 4. I will go through this quite quickly here. The error component we can calculate as AB times n minus 1, which is equal to 3 times 4 minus 1, which is equal to 27. And in total we have 36 observations in the experimental design, and we have 35 degrees of freedom in total then. Next step is to calculate the mean square, which is a variance measure. So to do that we take the sum of squares, divide it by the degrees of freedom associated with the sum of squares. So in this case 10,683.72 divided by 2 is equal to 5,341.86. So that's the mean square for material type. And we do the same for temperature and A-B interaction and the error component. Now what we're going to do now is to create an F0 value, which is basically a ratio between the mean square for material type divided by the mean square for error. So you can see 5,341.86 divided by 675.21. And this is equal to 7.91. And we do this for temperature and for A-B interaction as well. Okay, so a little bit more about the F-test, which is the next step. The F-test is, you can consider it as a signal-to-noise ratio test. The test creates a ratio between the mean square of a factor for a factor effect and the mean square for the error or noise. And this is a ratio between two variances, and this is why the ratio is F distributed. It can be shown that that's the case. Every ratio results in a F0 value. For example, the one that you just saw, but F0 is equal to, for the material type, let's say, is equal to mean square for A divided by mean square for error. Okay. So the F0 value is not worth too much to us at this point. One can say that the larger the F0 value is, the more likely it is that this effect is significant. The next step is to find out a p-value. But just before doing that, we have to understand how the F-variance ratio distribution works. So this is an example of an F distribution, and the shape of this distribution depends on the number of degrees of freedom you have in the numerator and denominator for the ratio that makes up the test. or basically the number of degrees of freedom for the mean square in the numerator and the number of degrees of freedom for the mean square in the denominator. And when you have the f0 value like this, then you can simply, you have the probability here that's left in the right tail. If you sum that, that's the p-value, or the probability that you will get an f0 value larger than this specific f0 value that you recorded. That's the p-value. The p-value can also be defined potentially as the smallest significance level that would have resulted in a rejection of the null hypothesis. So going back here, if this is really small, we can say that, well, a really small significance level would have resulted in a rejection of the null hypothesis. So this is why if we see a small p-value, this translates into this effect is probably significant then. Okay. So let's calculate the p-values for these f0 values. As you see, we have 0.002 for the material type and 0.0001 or less than that for the temperature, and 0.0186 for the AB interaction. So now we can compare these p-values with, let's say, a significance level that we're working on. Let's assume we work on 5%, then all of these significance levels, p-values, would have been smaller than that significance level, and we would have determined both main effects and the interaction to be significant. Even if we work on 1% significance level, then AB would be a borderline effect. It's larger than 1%, but it's quite small anyway. So it is quite reasonable to assume that we have effects of both material type and temperature, as well as an interaction effect in this example. Okay. So let's take a look at how a computer output from the Design Expert software would look like in this example. So it's very similar. There's only maybe two differences. One is the mean square for error, or error component is called pure error in the Design Expert software. And also we have in the software we get a summation of all the sum of squares for all components in the model. So material type, temperature, and interaction effects, they are summed up to a total sum of squares, total number of degrees of freedom, total or mean square for the complete model, and so on. So we get an f-test also for the complete model, but most of the times we're more interested in checking the like say the individual components of the model, like material type, temperature, and AB interactions, to see if they are significant or not. And we usually remove insignificant terms in the model. Okay, so finally then in this example, let's try to decide which material type that seems to be the best. That is to give the longest battery life over the different tested temperatures. This is not very trivial because we have this interaction effect, so it is useful to look at some of the plots from the software. So in these two plots you can see that well, we have an interaction plot here, and then we have sort of a plot with predicted values in the colored bars over the different tested material types and temperatures. And we have the longest predicted battery life is given for material type 2 and temperature 15 degrees. But even so, it seems that for the other temperatures, 70 and 125 degrees, then the bars are higher. So material type 3 is better for the other two temperatures, and it's quite close to the highest predicted battery life also for the temperature 15 degrees. So if we want to have a more robust material that's behaving not best at all temperatures, but more or less good in all temperatures, maybe the blue one, the material type 3, is the best material type in this example. Okay, so that has been a rather quick run through of the analysis of variance method for this factorial type or factorial design setting. So thank you for listening, and good luck with the analysis. Bye bye.